Welcome back. This is COT 3100. Today's topic is about complexity of algorithms. This topic is important just for us to understand what do we mean by complexity of algorithms and why is it important to understand it. And we will look at some examples and then we conclude this chapter by that. Complexity, usually when we talk about complexity of an algorithm, what we mean is for given a specific size of input, we want to know how long it takes for an algorithm, for a program to solve that problem. Okay, keep in mind the reason we are using computer are two. One, a good program, in other words, the reason we are using computer is the speed and accuracy. All right, so what's that telling me? That anytime I write a program, I have to be concerned about how fast the program that I write gets executed, and how little and how much memory it uses. As little as it uses, it's better. All right, and also the accuracy. For accuracy, that's the reason we come up with, for any specific program or problem, we come up with a number of algorithms depending on who writes it, right? We come up with a number of algorithms and then we pick the best one among those. And how do we pick the best one? We pick the one that solves the problem in the minimum time, the speed, the first reason we are using the algorithm, the computer. Number two, we look at them, how much resources a program requires. If it requires lots of memory, that's not a good program because it may cause, for example, a crash, right? Or may cause some problem in the hardware. So there are from two points of view, we look at the complexity. When we say complexity, we're talking about time complexity, and we talk about the upper limit. As we said, the input, if the number of the size of the input to a problem, if it grows, then we want to know how much it can grow and what is the maximum time it's going to take to execute. That's we call worst case complexity. And also we look at the space complexity, which means the amounts of memory required to execute as certain algorithms to solve a problem. Okay, so, but in this section, what we are really mainly concerned at this point is the time complexity, not the space complexity, because that gets very much complicated and it gets involved with a lot of other issues that's not in the scope of this course. So, given an algorithm, how efficient is this algorithm for solving a problem given input of a particular size, meaning the particular size of the inputs? To answer this question, we ask, okay, how much time does this algorithm use to solve a problem? Two, how much computer memory does this algorithm use to solve the problem? As I said, there are 2 points we look at. One is the time complexity, how long it takes. Two is space complexity, how much memory requires, how much resources is needed to solve that specific problem. However, we are concerned with the time complexity in this section. Time complexity, one of the ways that we do figure out, and one of the ways that we calculate the time complexity from the beginning, from the 20, 30 years ago, the beginning of this topic, is to look at the operations. For example, a loop operation. If a loop requires 200 times repetition, well, in the code it may look like 3 lines, but it is going to take like 200 times, right? Then we add up the number of times required to do that loops and how long it takes to do one of those loops. And then we add up all the other operations such as addition, subtractions, and we do not look at the specific things, your assignments and some basically cleaning or some housekeeping operations. We just look at these operations that takes certain amounts of time, and then we come up with a number. Then we compare it to another algorithm that solves exactly the same problem with the same size of the input and how long that one takes, right? This is how we compare these different algorithms, and we figure out which algorithms does the problem in a faster time, more accurately, and all of those things. But in this case, in our case right now, we are more concerned with the time, so we want to figure out which algorithm would solve it better. And that's the reason we studied the big O notation or big omega notation, big theta notation, because we need to know, as the size of the input grows, how fast this problem is going to grow and how much more time is going to require to solve the problem. That's why we need to understand the growth. We need to understand the growth, and we need to understand that will depend on g of x, which would be in this case the input, right? And if the input grows, how much this solution is going to require, how much more time it's going to require to solve the same problem. So what we do in these situations, we look at those problems, any algorithm, and we look at figure out what is the order. We use the big O notation or big theta notation, and we figure out how much it's going to take time, because that would give me how much this problem is going to grow, this function is going to grow, the algorithm, if the input grows, and then I can figure out exactly would be an upper level limit, and it's very easier to come up with the upper limit because it will depend totally on the order of those, how fast it is growing. Coming up with the average time it takes to execute a certain algorithm, it's a very complicated problem again, which is out of the scope of this chapter, right? At least we are not going to discuss it at this point. But how much it takes at the max in the worst case scenario to execute a certain algorithm, or we can evaluate. That's how we evaluate different solutions for the same problem to figure out which solution is the best solution for this given problem. Time complexity. To analyze the time complexity of algorithms, we determine the number of operations, such as comparisons, arithmetic operations, and all of those, the loops, all of those things, decision-making algorithms, operations such as if-then operations, because those, each one of them affects the number of times that one line of code or two lines of code may cause more operations at that same line. And usually the length of a program would not give you a good example of a good sample of the good indication of the time complexity, how much time it's going to require. What it gives you a good indication is to be able to count the number of operations that you have to go through within that maybe 10 lines of code, because I may have two loops embedded in each other and perform it with 1,000, 2,000, 10,000, 300,000 operations, right? For example, there may be a code if I want to recover somebody's password, for example, all right? If I know the password is a 6-digit number or a 6-digit number or 8-digit number or so many digit number for the alphabet embedded in it, I have to come up with an algorithm to try every possible combination, right? The code may be only 10 lines or 20 lines. But imagine how many times I'm going to go through this executing some of the lines, right? And that gives me the complexity of time. That's what we mean complexity of time. Or look at what I just said. It is like a set of numbers, right? Look at the long list in database, and I'm looking for a match. Is this name in this list, or is this number is in this list, or this case, certain specific information is in this list? And if it is, where it is, how many times it happened, and so you have to do comparisons, and that's what we looked at, those searching and sorting and all of those algorithms in previous lectures. Then what happens? Then we go through the list. Then it is totally dependent on the number of elements, the inputs, number of elements, and number of the operations. How fast am I going to find this input or this variable or this information in my list, or I'm not going to be able to find it at all. And if I'm not going to be able to find it at all, that means I'm going to go through comparing it with every single element in the list or in the database. So that's why the time complexity comes very handy, and we need to look at it. Let's take a look at some examples. And for example, in here, we are trying to find, we have a list, A1 through A sub n. There are n integers here, and we want to find the maximum element in a finite sequence, right? Finite sequence meaning I know what's the number of n. N is 10, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or there are 10, in other words, numbers in my list. And I want to know which one of these elements has the maximum value, since they are integers. And how do I do it? Well, I look over here, because first I want to find out what is it the function of. Once I know what is the function of, it is like if I'm coming up with an equation, like a polynomial, then I know the highest order in that function, the highest power number, is the order that it is going to grow. And here, basically, we are trying to count the number of comparisons. So we say, all right, we declare a variable as a max. We say max is equal to the first element. Then we start comparing it for I becomes 2, because we start comparing it from the 2 to all the way to n. Then we say if max is less than, for example, max in this case is A1. If it is less than A2, because it started 2, then max is, if it is less than, the max is A2. And then we go back, because we're going to repeat this one till I becomes all the way to the n, right? So the max is less than AI comparison is made n minus 2 times, right? Because it's one is itself, and then we start from the first element. And so we go n minus 2 times, depending on what's the value of the n. And then each time a is incremented, because I is from 2 to n, so I is being incremented. It starts with 2, then it becomes 3, then it becomes 4, all the way till n minus 1 compared with the n, right? That's why there's 1 here we are missing, we're not doing a comparison. 1 here, it's the 1, that's why it is n minus 2 times. Each time I is incremented, a test is made to see if I is less than or equal to n, because if it is equal to n, then we stop, right? And then you're not going to compare it to itself. That's one time, and then you didn't compare it when A1 was itself to A1, and so that's for 2 times. So n minus 2 times we made the comparison there, and one last comparison determines that I is greater than n. All right, I is greater than n. So so exactly, if I'm going to add all these numbers, because I'm going to make continuously comparisons, it is equal to 2 times n minus 1, which means it is, the time complexity algorithm is big theta of n, because it gives me the upper limit, right? Big theta of, and because this is the maximum that I'm gonna do the complexity test. And this is how we do it exactly for this algorithm. For example, determine the time complexity of the linear search algorithms. And we're going to compare one at a time and find out that if, remember the search algorithm, that we are searching for a certain input to see if it is in the list. All right. So and if I find that item in the list, then I return the location of that item in the list. If I cannot find it, I return 0, meaning it's not in the list. So I'm going to compare the whole thing. And again, this one comes to 2 times n plus 2, which is again n, it is theta of the n. And then you go, again, this one is going to be the order of big theta of n. Why? Because the highest order here is the n. If I had an n squared plus n plus 2, the order was n squared. And in this case, for example, again, at most became about 2k plus 2, and based on the value, because 2 to the power of k minus 1. Anyway, note that the k is equal log n. Let me, for simplicity, we are going to assume that n is equal to 2 to the power of k elements. And then k would be equal to what? Would be, if n is equal to 2 to the power of k, then k would be equal to log of n. So if it is log of n, and then we say it is the big theta of the log of n. And that's the complexity. You do not need to know exactly how this, I don't want to waste your time to explain the algorithm. That's not the part of this course, but I want you to understand what we mean by complexity. I go through the loop. I can do it manually, figure out how many times I did it, and then say, and what is that number? How many comparisons I made? And that relationship of that comparison with the n, right? Because you have a certain number of, here's the largest number is n, so you want to know, it depends the number of comparisons, that how many elements are in the list that you're searching, right? A sub n. So it is dependent on the number of elements in the search. So based on that value, I say, all right, this function, the growth of this function is truly dependent on the value of n, all right? And since this is a search, so I'm going to look at every one of them, every single one of them, and so I'm going to have to compare exactly how many searches I did. And in these situations, we know the time complexity, big theta of log of n. And where did I get log of n? We said the n is equal to the power of k elements. We assume that one. And anytime n is equal to the power of k, that means k, this power, is equal to log of n in the power with the base 12, of course. Well, in this case, it could be base 10, but we didn't say it here. So this is what we're talking about. And in this case, for example, what's the worst case complexity of a bubble sort in terms of the number of comparisons made? Again, we do the searching, and I'm going to show you these numbers in the next chapter, in the counting numbers. That's why I have a issue with explaining these things, because you don't know exactly why. For example, 9 plus 8 plus 7, 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 is equal to n times n minus 1 over 2, which means 9 times 8 divided by 2. That's what it means. All right. And but in this case, then if that is the case, then n times n is n squared minus n. then we simplify and it becomes n squared over 2 minus 1 over n over 2. What's the order of this, the growth of this function? It is really, it's the highest power. In this case, it's the n squared. So we say the worst case complexity of bubble sort is big theta of n squared. And so forth here. All right, we go through these things. I'm going to explain this hopefully this semester, so you know how we add up. And this is a simple mathematics that we need to discuss it so you can understand it. And again here, n times n squared minus n over 2 minus 1. What is the highest power? N squared. So we say therefore the complexity is big theta of n squared. And this was the insertion sort. And we go on. And again, we do the same thing for the matrix multiplication, complexity of matrix multiplication, which comes to the n cubed, by the way. It is the big O of the n cubed in this case, because the number of the comparison comes to n squared times n minus 1, and if you multiply them, it becomes n cubed minus n squared. Therefore, we say the highest power, it is the big order of big O of the n cubed. That means whatever the n is, let's say n is 3, it's going to grow 3 to the power of 3, 9. If n is 4, it's going to go through 16. And if you put that in a curve, you see it is growing kind of fast, way up. And how fast as the input grows up, as the n grows up, and we increase the value of n, the number of comparison is going up. And that's how we figure out why we need to know what is the complexity, right? For example, in n factorial, if you remember n factorial, the growth is incredible. Even in your calculator, up to a certain number, you can say 5 factorial, 6 factorial, 10 factorial. You get to one of those numbers that is not going to give you, because it grows so fast, the number is so huge that it wouldn't give you. So we need to know how fast it's growing, how the number of comparison is going to grow. So that gives me the complexity. That's what we mean, the complexity, meaning how long it's going to take. If I increase the input by tenfold, what's going to happen to execution time of this algorithm? It may grow so much that I cannot afford to use that algorithm anymore. I may have to look for another solution for that problem. All right. That's how much I want to discuss here. And we're going to move on to the next chapter in the next lecture. And I will end this lecture here. The chapter 3 will be basically is about the big O notations and the complexity and all of this sorting, searching, and all of these things, which is very important. All right, I'll see you in the next lecture.